A transit light curve looks simple. A star, then a dip, then back to baseline. But that smooth little valley contains everything: the planet's size, its orbit's tilt, its distance from the star, and the length of its year. Your job over the next few minutes is to learn how to read it, not as a layperson, as an astronomer. I am showing you a single transit, just the dip. No context, no star catalog number, no period. What physical quantities can you extract from this one curve? Pause and think. The answer is more than you might expect. Here is the light curve we are investigating, a 1.7% drop in brightness. The star looks normal, then dims by a tiny fraction, then returns. That depth is the first piece of evidence. It is proportional to the area of the planet's disk covering the star's disk. If we know the star's size, we can calculate the planet's radius. For a Sun-like star, a 1.7% depth corresponds to a planetary radius of about 1.4 Jupiter radii. Sit with that for a second. You have just produced a physical size, a real number of kilometers, for a world nobody has ever seen, from nothing but a dip in a graph. You still do not know which star this is. You do not need to. The geometry does not care. Now look at the shape of the bottom of the dip. Is it flat or V-shaped? A flat bottom means the entire planet disk is fully inside the star disk for a while. A V-shape means it just grazes the edge. The duration of the flat part versus the sloped part tells you the impact parameter, how close the planet passes to the center of the star. That, combined with the orbital speed, gives you the orbital distance. Watch the planet cross the stellar disk. Notice the gentle slope as it first touches the edge, that is ingress. The flat middle section is the full transit. The second slope is egress. The length of the flat section compared to the total transit duration is a direct measure of the crossing geometry. A short flat section means a grazing transit. You have one dip. It could be a planet in a 3-day orbit or a 30-day orbit that happened to transit. Only by returning to the same star night after night and seeing the dip repeat at a regular interval can you lock down the period. Kepler stared at one patch of sky for 4 years specifically to catch this repetition for Earth-sized planets. Here is a test. A flat-bottom transit repeats every 3.5 days. What is the semi-major axis of this planet? Pause the video and commit to an answer. Actually commit. The correct answer is B, about 0.05 astronomical units. That is incredibly close to its star, well inside the orbit of Mercury. A 3.5-day period tells you the planet is practically hugging its star. That star has a name, by the way. HD 209,458, the first planet ever seen to transit its star. You just re-derived, in 90 seconds, what took a team of astronomers a full observing season in 1999. First, the depth gives you the size. A 1.7% dip means a planet roughly 1.4 times Jupiter's radius, as long as you know the star's radius. Second, the shape, the slopes, and the flat bottom tells you if the planet crossed the center or just grazed the edge, and that leads directly to the orbital distance. Third, repeated transits lock down the orbital period, and with Kepler's third law, the semi-major axis. You now have the 3 core quantities: radius, orbital distance, and period. Next lecture, we will explore why Kepler stared at the same 150,000 stars for 4 years straight, and how that stare transformed our understanding of the galaxy.